Hello, everyone. Welcome back. Today, we're going to be talking about reductions and Grignard reactions, which are both going to actually share quite a few similarities. So, last lecture, we talked about taking alcohols, performing reductions using Jones reagent or PCC to essentially lose some hydrogens, right? Because it was the hydrogen down here that actually mattered. So, you can imagine that if we're going to do some reductions, we're going to essentially need to gain some hydrogens, right? So essentially what we're trying to do is we're trying to do the opposite of an elimination, right? And that's where our reductants come in. So we have two major reductants that we're going to be focusing on today, um, for OChem specifically. And those are the first one, which is our weak reductant, sodium borohydride, NaBH4. And then we have our second one, which is our strong reductant. And it's called lithium aluminum hydride, or LiAlH4. So, to preface these guys, the first thing that I would like to point out to you is when you think about something like methane, right? Just a carbon with some hydrogens, and you think about the way these bonds are polarized, right? We would say the carbon is pulling the dipole. So essentially, the hydrogen is partially positive and the carbon is partially negative. But what we're saying whenever we want to do a reduction is we want to actually add in a hydrogen in a nucleophilic sort of way. So how would we do that? Well, that's where these reductants come in because they have a very interesting special property. If we look at something like sodium borohydride, we have, that sodium with a positive charge. Then we have our boron connected to these hydrogens. But in the case of boron, right, it's actually less electronegative than hydrogen. So what this is actually doing is the dipole has now switched directions. Where in the case of the boron hydrogen bond, the hydrogen's taking the partial negative and the boron is taking a partial positive. So essentially, this is the most important part of this type of reagent. Since that hydrogen is more electronegative than the boron, it's partially negative. And you can imagine if we're comparing these two ideas between what is a partially positive hydrogen attached to a carbon and a partially negative hydrogen attached to a boron, we're essentially thinking about two different species. Because something like an H plus, we've talked about in the past, right? This is a proton, essentially. And protons are Lewis acids, right? Whenever you think about acid-base chemistry and protons being plucked off of things, it's normally because they're forming a bond by something giving electrons to the proton. On the other hand, if it's a negative charge, this is called a hydride, right? Think about what we talked about in terms of rearrangements. They were called hydride shifts because it was the hydrogen that was using its electrons to move around. These are more Lewis basic, right? So these are Lewis bases, aka nucleophiles. Okay? So if we're looking at hydrogens as a hydride, we are essentially saying we are using H minus as a nucleophile. And before we look at how this is used as a nucleophile, one thing that I want to point out is looking up here at our reductants, I did label one as a strong reductant and one as a weak reductant. The question is why? Well, if we look at the structures between these, the salt that we're forming, that counterion matters a little bit, but more important is actually the structure that is attached to the hydrides itself, right? Because looking at these, we see that the difference is the aluminum versus the boron, right? Because we also just have our sodium chilling off to the side and our lithium chilling off to the side. So what is different between the aluminum hydrogen bond and the boron hydrogen bond. Well, one thing you got to keep in mind is the size, right? Boron is one of the earlier elements on the periodic table. So when we think about the size of boron, it's rather small compared to the size of aluminum. And what this means is those little hydrogens that are attached are much further away from the nucleus of the atom. And so it's a little bit weaker of a bond. And by a little bit, I actually mean quite a lot. So since aluminum is bigger than boron, it has weaker aluminum hydrogen bonds. The other thing to keep in mind is their electronegativities. If you look at aluminum versus boron, where are they on the periodic table? Well, they're actually right on top of each other, right? Because it's boron, carbon, nitrogen, oxygen. Just below boron is aluminum, just below carbon is silicon. So where it sits on the periodic table, just below boron, it is also less electronegative, right? Because the further down and to the left you go on the periodic table, the less electronegative you get. So aluminum being less electronegative than boron also means that in terms of our hydrogen, it is going to have a bigger partial minus, right? So we'll write that out as well. So essentially what we're saying is the bonds are weaker and the hydrogen has more negative charge, which means that essentially this is a stronger H minus overall. Okay, so let's see how these things actually work in action. And we're going to mostly focus on using lithium aluminum hydride today because the mechanisms and the way they work will be the exact same between the two with some exceptions. So, looking at something like this ketone, right? Let's say we took this ketone and we exposed it to some lithium aluminum hydride in a nice solvent like THF. The second thing we'd have to do is we would have to do another workup step, just like we were doing in the previous nucleophilic acyl substitutions. And it'll become apparent why in just a second. This will end up forming our alcohol, right? So how does it do it? Well, if we take a look at our mechanism that we're going to show down here, what we see is our ketone, as we talked about last time, has a partial positive charge on the carbon and a partial negative on the oxygen. Our lithium aluminum hydride, which is primarily driven by the aluminum hydride piece of this, is going to come around and do a nucleophilic attack of the hydride into the carbonyl carbon. Now, this looks a lot like those nucleophilic acyl substitutions we were doing. The only difference is there's no leaving group in this case. And the thing is, that's actually good for us here because we're forming a carbon-hydrogen bond, right? And that carbon-hydrogen bond is essentially not going to form a good leaving group. So now we've kicked up the electrons to the oxygen, but there's nothing that we can kick back out. So it can't just fall apart like normal and generate a new carbonyl. Instead, it's stuck like this with the single bond. So from here, we now have a Lewis base oxygen, and we have a Lewis acidic aluminum. So we can do a Lewis acid base reaction that complexes and associates the oxygen to the aluminum, right? This is classic. It's what we talked about quite a while ago in one of our previous lectures that was related to acid-base chemistry associations. So from here, this is the end of step one, right? This is the step one product. There's nothing else that we can really do from this point because we've already taken the double bond and it's already been added into. There's no more good electrophiles. So from here, what we do is we add in that HCl and water, and essentially we formed hydronium as an acid. And so from here, we use the electrons from that aluminum oxygen bond And essentially, we're breaking that bond, giving the electrons back to the oxygen, and that's then doing a subsequent acid-base reaction that gives us the alcohol, right? Essentially, it's the same idea as if you took the reagent that was shown right here in the middle and also exposed it to the HCl and water. But the importance of why the aluminum's there is going to come in handy a little later. But this is how we get to our alcohol, right? It is through that nucleophilic addition. So you may notice that this does have a lot of similarities to that nucleophilic acyl substitution we were talking about last time, right? We're adding into the carbonyl, and then some other stuff is happening, but in this case, since there's no leaving group, there's nothing else we can do. So if this is how we reduce carbonyls, same mechanism applies if you're using sodium borohydride. What happens if we take it a little further? Because this is just a ketone. What if we took it to something like an ester? Because we saw esters last time were a little funky, and this time they're going to be a little funky as well. Let's say we took some lithium aluminum hydride in THF, did a workup step with HCl H2O. What would you expect you would receive from this? Take a moment to think about it. And then whenever you have your answer, you can unpause the video. What you should have thought, but what may not have been immediately obvious, is you will actually end up with a primary alcohol and methanol. So how does this one happen? Well, funny enough, the nucleophilic acyl substitutions have already prepped us for this. If we take a look at what the mechanism is going to look like for this type of reaction, what we'll see is that just like beforehand with our ketone, the first step is going to be the hydride adding to the carbonyl and kicking those electrons up to form the oxygen with the negative charge. Upon adding in this hydrogen, we have generated this intermediate. This intermediate is more stable than our lithium aluminum hydride because remember, it's kind of like an H minus. And so if we go from an H minus to something with an O minus, that's good. Here's the thing though. When we're looking at this, this is not going to be as stable as if these electrons drop down and kick out this oxygen. And the reason for this is you can imagine that by kicking out that oxygen, we have now gotten an entropy benefit because we have generated more molecules than what were in that tetrahedral intermediate. So from here, we now have this methoxide that's sitting around, and keep in mind our aluminum is still in the solution. So what's going to happen is this methoxide is going to come in and it's going to make a complex and associate with the aluminum to generate a new negatively charged aluminum complex, such as this one here. Now here's the thing. This looks quite a bit like lithium aluminum hydride, the aluminum hydride part, just with an oxygen now attached. So what that means is that something like this hydrogen right here is still available as a nucleophile. And wouldn't you know it, in the middle of our reaction, what is this right here? It's another carbonyl, right? It is an aldehyde. And so what's going to happen is essentially that aldehyde that we just formed can be reacted with the same aluminum hydride because it has more hydrides to give. And so that's why whenever you're looking at this, it actually ends up generating now a second addition of the hydride to make this negatively charged oxygen here, along with your aluminum species, which of course this will then coordinate to. But I'm not going to show that step because I already showed it up top. Instead, I'm just going to say HCl H2O because we know that's going to end up protonating our alcohol. And then it also ends up protonating that methanol that was attached to the aluminum. What this means, though, for our overall reaction is if something more stable than H minus can leave, It will, right? It's following that same idea that the nucleophilic acyl substitutions were, but now we're using an even better nucleophile that can't act as a good leaving group, so it's much harder to kick it out. So let's apply this now to another example with something like amides, right? An amide at this point, you may think is going to act very similar to the ester, right? If we add in our lithium aluminum hydride in THF, and then we follow it up with HCl and water, what do you think we end up with? Well, the answer is actually an amine. So that might be a little bit of a surprise, but it makes a lot of sense if you look at the mechanism. So thinking about the mechanism here, it always starts out the same. Our hydride is going to come in and do a nucleophilic attack to add in to the carbonyl carbon. At this point, we generate that same intermediate that we've been looking at many times before. But here is the kicker. The nitrogen is still a bad leaving group, right? This is still a very bad leaving group. So it does not want to leave. What's going to happen in the meantime is we still have that aluminum in solution, right? And this is the reason the complexation is actually important. Because if this forms an associated product with our aluminum, what we've just done is we've made a neutral oxygen species. And what's good about a neutral oxygen species? Well, it's a better leaving group than the nitrogen. So if it's a better leaving group than the nitrogen, then it's going to be the one that actually leaves. So the nitrogen in this case is going to be the one that forms that double bond to fulfill the octet that would be missing if the oxygen left on its own. And this is what generates this intermediate right here with the positive charge on the nitrogen. And then this is followed up by some more aluminum hydride coming in, whether or not it's the same as the one that just left with the oxygen, or if it's just a completely new one, and adding into that amide right there. Now, that being said, this isn't exactly what we end up seeing, because there's probably an acid-base reaction that happens before this, but it essentially gets across the point, and I'm not going to ask you for this mechanism much on the exam. So essentially, what we're looking at here is the leaving group is still dependent on how stable it is. And since we can get rid of the oxygen, that's more important than having to get rid of something like that nitrogen. So with that being said, if we think about reduction, it's a little more complex than oxidation, because oxidation, we really only had two ways that we could go. Instead, with reduction, we're going to have multiple different thoughts that we need to do when we're thinking about the products that we generate during these reductions. So we'll split it into two categories, sodium borohydride and lithium aluminum hydride. All right, and we'll check based on functional group what product would actually be made by these two reducing agents. All right, so let's start off and let's look at an aldehyde. Right? It should be pretty obvious these two are going to generate the exact same thing, right? They're going to take that, they're going to add in their hydride, they're going to make the primary alcohol, right? It is no different between the two. What would happen if we did it with a ketone? Well, surely that's not going to make a difference, right? They're still going to do the same thing. They're going to add in their hydride. They're going to end up making secondary alcohols. Here's the thing, though. As we start going down the line, we're going to end up getting a very interesting switch in what these things can do. Because if we try and do something like an ester, what we're going to see is that sodium borohydride has no reaction. And this may be a little bit of a surprise because I did say that these are relatively similar. They don't do much different. The thing that is different, though, is since sodium borohydride is weaker, right? Let's return back up here and look at our little diagram. It has weaker hydrides. That means it actually has trouble reacting with some carbonyls. In this case, for an ester, the ester is not reactive to sodium borohydride, but we've already seen with lithium aluminum hydride, it makes the primary alcohol. Right? What about something like a carboxylic acid? Well, interestingly, unlike many of the things that we've been looking at, carboxylic acids can be reduced, but they cannot be reduced by sodium borohydride. We're going to see no reaction. On the other hand, lithium aluminum hydride will treat it the exact same way it treats esters, and we'll end up with a primary alcohol. Okay? Another type of carbonyl that we just talked about is an amide, right? Looking at the amide, funny enough, sodium borohydride has no reaction, but lithium aluminum hydride does, and it forms the amine. Lastly, another one that we haven't talked about, and it's not really a carbonyl, but it acts a lot like one, is a nitrile, right? That carbon triple bonded to a nitrogen. And if you had to guess what's going to happen here, I'll tell you right now that sodium borohydride is no reaction, but lithium aluminum hydride makes the amine. Right? And that's just through multiple additions of our hydride. Now, this may make it seem like sodium borohydride is completely useless, right? Because why would you want to use something that can only do aldehydes and ketones, but then lithium aluminum hydride can do everything, so why not use it? Well, I'll give you an example. Let's say that you had a molecule that looked like this. And you really wanted to take this molecule and run it through a reduction in order to get one primary alcohol so that you can do some reactions. Well, if you think about it, if this were to be run through a reaction with lithium aluminum hydride and THF, what exactly is going to happen? Well, we know, just based on what we've talked about in that table above, that we have currently on this molecule an aldehyde and an ester. The aldehyde is going to be reduced, as we see up here, to a primary alcohol. The ester will also be reduced to a primary alcohol. So what we should see with a reaction with lithium aluminum hydride is that we end up in the situation where the aldehyde and the ester both make alcohols. But if you didn't want to have the two alcohols, let's say you instead used sodium borohydride and something like THF, and then you did your HCl H2O workup. Well, based on sodium borohydride's reactivity, it can't do esters. So what you would actually end up with down here would be the aldehyde would still convert into the alcohol, but the ester would remain untouched. So we would say, by comparison, sodium borohydride is more selective for some carbonyls. So in reality, it could be useful to have sodium borohydride in your solution if you want to reduce one carbonyl over another. Another really important thing, though, is when we're looking at these two reagents, one other difference they have is their ability to do acid-base chemistry. And the reason I say this is because if we take a look at something like this here, if I were to put this through a reaction with lithium aluminum hydride, and let's say I did not add in the workup step of actually reprotonating everything after it was all said and done, what we would end up seeing is this as our product, right? And the reason for this is because lithium aluminum hydride is basic, right? So before actually reacting with the ketone, what lithium aluminum hydride would do is the alcohol, which has an acidic proton, would come into contact with our lithium aluminum hydride, and the hydride would actually grab that as a uh, acid-base reaction to generate the alkoxide. Okay? That cannot be said about the same with sodium borohydride. If you were to expose this to sodium borohydride and something like we were saying, THF, you would end up seeing that the product would still have the alcohol. It would just have that as the O minus. All right? And the importance here is that means that this solvent that we're using for sodium borohydride doesn't have to be aprotic, which is nice because it's a little easier to use in lab. Now, with that said, this basicity will matter more right after we talk about these Grignard reactions. So hold up a second in terms of thinking about why this is going to matter too much because this example doesn't seem as useful as the one right above. But with that being said, let's hop into Grignard reactions. So these reactions are based on the same principles that we just did with those reductions. So they're similar to reductions with hydride, but we are adding carbon instead. So how is that even a possibility? Well, it all comes from this type of reagent right here called a Grignard reagent. And you'll notice this looks very different from anything that we have been looking at thus far. It has this weird magnesium, bromine, and then it also has the magnesium bound to a carbon. Whenever we look at this structure, the first thing that I want to point out is the carbon has an electronegativity of right around 2.5. All right. The magnesium has an electronegativity right around 1.3. This difference is huge. All right. It's a large difference, and it's practically ionic. Okay. And so what this actually looks like if we were to draw this as a more representative representation, it would be a carbon with a negative charge that's chilling out with this magnesium bromide that has a positive charge. All right. And looking at a carbon with a negative charge, you may be able to tell right away that this is a very strong nucleophile and base. The thing is, though, it's both of those things. Where it's the most nucleophilic is towards carbonyls. So if we take a look at something like a ketone and we run a reaction with something like this Grignard reagent that we're presenting in THF, and then we work it up with some HCl and water, what we're going to see is we actually generate something that looks like this. We generate a tertiary alcohol. So how does this happen? Well, if we look at what the mechanism is going to look like for this, Essentially, it's the same as our hydride additions. But here it is the carbon from the Grignard, right? Because this is the better representation that's coming around and adding in to our carbonyl and pushing those electrons up to the carbonyl oxygen, right? What this is doing is it's forming this new carbon-carbon bond, right? And the one thing you got to keep in mind about these Grignard reactions is make sure you really count the carbons that you're adding in. Because in this case, we're adding in two carbons. So off of that carbon that we just added to, we should still have one and two carbons. Now, that being said, we're left with this oxygen with a negative charge. But again, we have to think to ourselves, are there any leaving groups here? No, right? Because what we've done is we've formed a very strong CC bond. And that surely won't be leaving as a leaving group. And clearly this reaction is favorable because we go from a carbon with a negative charge to an oxygen with a negative charge. All right? Overall, we would say that the oxygen's much happier because it is much more electronegative. So this would be the end of the first step, which means that the second step would just be that workup with the acid. And of course, that workup with the acid, as we've been discussing, ends up forming our alcohol in the end. So it's super similar to everything we've been talking about. It adds in, and then you have to protonate it afterwards. But the thing is, just like hydrides, just like everything we've been looking at beforehand, there's some funky things that can happen with leaving groups. All right? So let's once again look at what happens with esters. So if you can't tell, esters are a relatively versatile functional group, right? Making them is also very easy. From those acyl halides, you just add in something like methoxide. And the thing is, from there, it can derivatize into multiple things. Let's say that we added this methyl magnesium bromide or the methyl Grignard reagent, and we do two equivalents. That's going to be important for a reason that we'll look at in just a second. If we do this, what we're going to end up generating is actually going to be shown to us in a mechanism down here. So let's draw out the mechanism to determine what the product would be of this reaction. Well, just like happens with everything else we've been working on, if this methyl has the positive charge or the negative charge, it's going to act as the nucleophile. It's going to come over here and it's going to nucleophilically add to that carbonyl. From here, so we've installed this CH3, that's what that methyl was, and now we have that O minus, right? At this point, it's the same idea that we were talking about for the previous reactions that we were working with the hydrides. We've added in something that can't act as a leaving group. But what can happen is we can reform this double bond primarily because it's entropically favored, right? Enthalpically, it's very similar, but entropically, it's very happy. And so we've kicked out this methoxide, okay? From here, though, we still have another equivalent of this methyl magnesium bromide, right? This Grignard. And that can come on in and it can add into this ketone that we've formed. Because once we've kicked out that methoxide, since we added in another carbon, we're sitting at a ketone. From here, we have now generated a tertiary alkoxide. And as you can imagine, this is the end of step one because we no longer have any leaving groups connected to that carbon. So from here, it's just going to be as simple as that acid workup step, where we have that H3O plus that we grab a proton from, and we form the tertiary alcohol. Okay? So this has everything in common with the hydride additions. The only difference is since we're adding carbons, it changes the type of functional group that we end up with. Because if we added two hydrogens through a reduction, we end up with two hydrogens attached instead of two carbons. So it's a primary alcohol. But then if we do this Grignard reaction, we end up making the tertiary alcohol because we're adding carbons. Okay, that being said, There is one thing that these Grignard reagents do struggle with, and that is the fact that we got to beware of acidic protons. Just like lithium aluminum hydride, Grignard reagents are also very basic. And so let's say we wanted to take a carboxylic acid and we tossed in our Grignard, but we only did one equivalent because we were not feeling like going too crazy. Right? That in THF, and then one or for our second workup step, HCl and H2O. What would happen? Well, essentially, thinking about this, we have a very acidic proton and we have a very good base. And that leads to, of course, acid-base reactions happening. Because remember, acid-base reactions are some of the fastest reactions that can actually occur. So if it can occur favorably, it will. And since this carboxylic acid forms the very stable conjugate base of carboxylate, you can imagine that's going to be quite a bit more stable than our negatively charged carbon. So essentially, we add on a hydrogen to our Grignard reagent. And since we only have one equivalent, with no more Grignard, we essentially see no more reaction. That being said, if we had another equivalent of Grignard, we could actually do something, but we can't here. All right? So usually Grignards aren't used with carboxylic acids because then in the HCl H2O workup step, you just end up protonating your carboxylic acid and you have remade the exact same as what you started with. All right. So beware of your acidic protons because essentially they will take Grignard right from under your nose. All right. I promised earlier that we were going to talk a little bit about why that basicity with lithium aluminum hydride and Grignards is useful. That is this point. And it has to do with epoxides, right? Because funny enough, these things can also do epoxide openings. So we're going to look at what that does. Essentially, when looking at these epoxides, they're going to act very similarly to what we see in these carbonyl reactions, right? If we were to take lithium aluminum hydride in THF, since lithium aluminum hydride is so basic, it's also a really good nucleophile. And so we're essentially putting this epoxide under a base catalyzed epoxide ring opening, right? Where the base in our nucleophile happens to be hydrogen in this case. So what we actually form in this case is this new bond that I've shown in blue between the hydrogen and the carbon, and we now have the alcohol from where the epoxide opens. The same thing can be said about Grignards. If you run a Grignard reaction with an epoxide, what you'll see is that this time we'll also add in, but we'll add the carbon chain in, which I have also put as a blue line for the new bond formed. Right? And you'll notice that for both of these, they've added onto the primary side of the epoxide, right? Because that is the less substituted side. And it's all because these are technically basic. So if we want to look at the mechanism on how this happens, keep in mind it's going to be the same for both the lithium aluminum hydride and the Grignard. So I'm only going to show the Grignard in this case. You can imagine if that Grignard comes near the epoxide, it's going to come around, do an SN2 to kick out the oxygen, and that will have formed that carbon-carbon bond where we're adding on those two carbons to the right side of the molecule. From here, the only thing that we're doing is another acid workup where our negatively charged oxygen can grab that proton and we can end up forming that alcohol. All right. So this first step here is exactly the same as base catalyzed epoxide ring openings. So it does SN2 on the least substituted side. All right. So essentially, whenever we're looking at these Grignards and lithium aluminum hydride, they both do these very specific reactions, right? One of them will always, or well, they'll both do reactions with both carbonyls and epoxides, but essentially with carbonyls, um, the lithium aluminum hydride will add a hydrogen to make less substituted alcohols, and then the Grignard will do addition to make more substituted alcohols because it'll be adding carbons. All right. And then on top of that, they can add on to these epoxides where one of them adds on the carbon chain and the other one adds on hydrogens. So with that being said, when we look at Grignard reagents, I do also want to give a table here. That way, everyone is comfortable with it. For our Grignards, essentially, if we take a functional group and we react it with a Grignard, what are we going to see? Well, in the case of things like aldehydes, we are going to end up seeing the full addition, right? We will essentially end up making the alcohol, and we'll also end up with some R group where we're going to assume in this case the R group is just an alkyl chain. All right. In the case of ketones, it's going to be very similar, where we're going to form an alcohol. This time it's going to be a tertiary alcohol because the R group that we have substituted is also an alkyl chain, and there were already two carbons attached. In the case of an ester, what we're going to see is we will have multiple additions of the R group because we will have kicked out that O methyl down there. In terms of amides, right? This one is also one that does ABC. So it's not applicable, right? You can't really run Grignard reactions on amides. And then same thing with carboxylic acids, right? Oh, whoops, I was drawing the conjugate base. Because these also just do acid-base chemistry, right? And even with excess Grignard, I think I said up here it could do more. That is not the case. I apologize if I did say that, because essentially once you form that carboxylate, it's not the Grignard's not nucleophilic enough to attack anymore. So essentially, it's just going to do acid-base chemistry on those. So Grignard reagents can really only do these top two. It's very similar to how far sodium borohydride can go, but it can do esters, which is a little better. So with that being said, this was our adventure into a lot of carbonyl chemistry, and this will prep you very well for second semester. But now we're going to do another pivot, and we're going to start looking at alkene reactions. And so these alkene reactions are going to use some of what we've learned here in order to help generate alkenes. That way we can then react them and use them in different ways to do syntheses. I'll see you next time.